Okay, this is part 6 of the stellar structure and evolution unit. Let's recap so far what we've talked about. We said that stars with an initial mass of less than 0.4 solar masses, less than 4/10 of the mass of the sun, will never go through a giant stage and will eventually just collapse in on themselves when they run out of hydrogen fuel and become a white dwarf star. Okay. Now, none of this has ever happened because these stars have not had enough time to evolve to that state. But we think the theory is sound, and we're pretty sure that that's what's going to happen. A medium mass star, anything between 4/10 of the sun's mass up to about 8 times the mass of the sun, those stars will go through a normal giant phase. They will extend their lives by burning helium in their core and hydrogen in a shell. But once the core runs out of helium, it is contaminated with carbon, and we don't think these stars will ever get hot enough to burn carbon in the core. And so the core will shrink down to a white dwarf. At the same time, the envelope is being blown away by a massive stellar wind to become a planetary nebula. This nebula will dissipate into space, and eventually what you'll be left with is a white dwarf. The really interesting part happens when you talk about stars greater than about 8 times the sun's mass. Okay, when it's more than 8 times the sun's mass, stars can go through the carbon burning phase, and depending on the initial mass, they can go through many, many other phases of nuclear fusion. They can burn heavier and heavier elements and create heavier and heavier elements up until they create iron in the core. Iron is a contaminant in the core that cannot be burned for fuel. Every other waste product, it's possible to burn as long as you get things hot enough, but iron refuses to give off energy when you try to fuse it. In fact, what happens is it sucks up energy. So once you have this instability with a core that is contaminated with iron, there's a giant collapse of the core. The core implodes, basically, and you have an incredible chain wreck. The implosion happens at a good fraction of the speed of light. It only takes a few milliseconds for this to occur. The rebound blows the star apart, and you get what we call a Type II supernova. A Type II supernova turns out as much energy in a second as the sun does in its entire lifespan. It's just an unbelievable amount of energy. These supernovas can briefly outshine entire galaxies of hundreds of billions of stars, and they stay bright for many, many months, and then or for several months, I should say, and then they fade away, leaving behind a very interesting object. But before we get to that, I just want to mention what the importance of these Type II supernovas are for basically our existence and the existence of our solar system. We will see later on in the course that the universe started out as being made up of primarily hydrogen and helium. About 3/4 hydrogen, about 1/4 helium. And there were just trace amounts of maybe lithium and beryllium, and certainly no heavy elements like iron and carbon and oxygen and nitrogen, the things that make up the world around us. No silicon that makes up rocks, that sort of thing. The only place we know of that those materials can be created is in the inside of stars. And if stars just shrunk to white dwarfs, we wouldn't get many of these heavy elements scattered about the universe to make new stars and perhaps planets. So we would only have a universe made of almost entirely hydrogen and helium. That's not a very interesting universe. You can't make things like a planet or a car or a tree or you and I with just hydrogen and helium. You can't even make a periodic chart in the front of a classroom because you wouldn't have a chart, you wouldn't have a classroom. You need heavier elements to make interesting things. The way those heavy elements that are made inside of stars that burn elements up until you get to iron, the way they get scattered throughout the galaxy is through the explosion of supernovas. And the way that all the elements beyond iron, things like lead and silver and gold and uranium, the way those things get created is in those brief 30 seconds or so of the supernova rebound explosion. And then they get scattered into the galaxy, mixed with other gases and dust, and then eventually coalesce into other stars and eventually other planetary systems. So supernovas are responsible for the synthesis of all elements in the universe heavier than iron. And since you and I are made up of elements certainly heavier than helium, carbon, calcium, silicon, well, a little bit of silicon, oxygen, nitrogen, organic molecules, which are carbon-based. These heavy materials, these building blocks, are the building blocks of you and I. So the ashes of explosions form these supernova remnants, which then dissipate through the galaxy. They enrich the interstellar medium with heavy elements, and almost all of the atoms that make up the Earth and our bodies were once manufactured inside supernova explosions that happened billions of years before our solar system formed. So in other words, you and I and the Earth around us, and everything in it, except for the hydrogen atoms on the water molecules, that's about the only thing that was not made inside supernova explosions or inside other massive stars. All of these things are stardust. So you and I and the world around us are made primarily of stardust, with the exception of the helium and hydrogen. Okay. Well, some of the helium was made also in those explosions as well. I think this is probably the closest connection we have to our universe. So that begs the question, well, what happens to the core of the exploded star? Is that gone as well? In most cases, no. In most cases, it leaves behind one of two possible remnants. And that, of course, depends upon, well, you guessed it, mass. Mass is the most important input parameter of a star. And it pretty much, if you know the mass, you can almost entirely predict the future history of a star's existence. Okay, so the fate of the core that remains after supernova also depends upon its mass. There's a very special number, 1.4 solar masses. That is called the Chandrasekhar limit because it was discovered by an astrophysicist named Chandrasekhar. And it turns out that if you have a remnant core of a star or a collapsed star with less than 1.4 solar masses, it will remain a white dwarf. The electron degeneracy pressure will be strong enough to hold it up. But once you get past this magical limit, the electrons are no longer strong enough to hold the white dwarf up. The white dwarf has this little trick. If you add a little mass to it, it will shrink and become more dense, and that will cause the electrons to have a little more strength to hold up the star. But once you get past 1.4 solar masses, because of relativistic effects, the electrons are no longer strong enough. They get injected into the protons and neutrons and it becomes impossible for the star to hold itself up. So a core heavier than 1.4 solar masses has two possible outcomes, a neutron star or a black hole, because gravity will win the battle. Certainly will win the battle over the electrons. Okay. So we think that the range of masses, of core masses, now we're not talking about the initial mass of the star here, we're talking about the remaining core. If the remaining core of the star is somewhere between 1.4 times the mass of the Sun and 3 times the mass of the Sun, we think you end up with something called a neutron star. Okay. So as I already said, the degenerate electron pressure will not support the core if it's greater than 1.4 solar masses. Gravity will just be too intense. The star will try to shrink to increase the strength of the pressure, but that won't be enough, and the star will crash through the white dwarf stage. The electrons will be forced into the protons, and a process called inverse beta decay will occur to form neutrons. The entire core is basically turned into neutrons. Now remember, neutrons are these subatomic particles that we have pretty much in every atomic nucleus except for hydrogen. And even some, there's even an isotope of hydrogen that does have a neutron called deuterium. So neutrons are in almost every atomic nucleus there is. They're a lot like protons. They're heavy. well, relatively speaking. They're almost the same mass as protons, but they have no electric charge. And once the entire core is turned into neutrons, the collapse continues until the neutrons are nearly touching each other. And when that occurs, the neutrons get claustrophobic. Okay, now of course claustrophobic is sort of an analogy here. I'm not talking about neutrons actually getting nervous and agitated. But they do get agitated. And the reason is neutrons follow quantum laws just like electrons. And if you pack too much of them into a small space, they set up energy levels, and you end up with only 2 neutrons to an energy level. And that means some neutrons are going to be pushed up to very, very high energies. So that means that they're going to be wrangling around, they're going to be bouncing off the wall, so to speak, with very, very high energy. This is called degenerate neutron pressure. Degenerate neutron pressure is stronger, much, much stronger, than degenerate electron pressure, mainly because neutrons are much more massive particles. And so degenerate neutron pressure, these overcrowded neutrons, halts the collapse. But by the time it halts this collapse, the core of the star is only about the size of a medium-sized town or city. The core is then a neutron star. It's maybe 10 kilometers, which is roughly 6.3 miles in radius, roughly 12 to 13 miles in diameter. That's insanely small. You're packing the mass of an entire, well, from 1.5 to 3 solar masses into a tiny ball the size of a city. The density is 10 to the 15th grams per cubic centimeter. That's just unimaginable. Basically, a teaspoonful or a sugar cube of this material would weigh 5 billion tons. It would weigh about as much as Mount Everest, let's say, or a typical Alp or a Rocky Mountain. So imagine taking a giant mountain and crushing it to the size of a teaspoon or a sugar cube. That's the kind of material that neutron star material is. It's unbelievably massive. If you dropped one of these things, if you could somehow pick it up so that you could drop it, it would crash through the Earth's surface and go right through the Earth and punch many, many holes as it oscillates back and forth until eventually friction would stop it. Now, because of something called conservation of angular momentum, and the most common example of conservation of angular momentum is when an ice skater throws herself into a spin at the end of her program. She'll start with her arms and one leg outward and then pull the mass in toward the center and spin very, very, very fast. That is called conservation of angular momentum. Whenever you have a spinning conglomeration of material that gets closer and closer to the center of spin, the speed of the spin will increase to keep the angular momentum the same. And what that means is if you have a star that is slowly rotating and it collapses or contracts to a much smaller object, then it will end up spinning much, much faster in the process. So due to conservation of angular momentum, a neutron star should spin very rapidly indeed, because it's pulling in a ridiculously large amount of mass into a ridiculously small sphere of matter. In fact, if the sun could somehow magically contract to the size of a neutron star, it would spin once every 1,000th of a second. So the sun would be spinning at 1,000 RPS, rounds per second. That's just unimaginably fast. But we think that there are actually stars that do that. But I will save that for part 7 of our unit.